Right, anyway, hello, I'm Steve Bazire. I used to work for the Trust, Mental Health Trust that was in Norfolk, but I've retired from the NHS now, so I'm just me. But I've got an honorary thing at UEA and I run some businesses. I'm trustee of Norwich's Central Norfolk Line, which is different than the Suffolk Line. Hi. So there we go. I always start by putting my declarations of interest up, just to show I do a bit of work for the pharmaceutical industry. I am a bit of a tart, but I'm not a prostitute, so I don't change anything I say just because someone's paid me to do something. But this is in my own time. I've even paid my own petrol money from Norwich to here, and my own car parking. Well, I've got a sandwich anyway, so that was all right. Makes it all worthwhile. And also, of course, a lovely group of people here. So now, what I was going to do, and I haven't got too long, have I? I've got half an hour, is it? Yeah, okay, I'll work through that fairly quickly. Is just to go a little bit about the brain itself, about how it works, and then how the medicines that can help treat dementia and memory impairment and Alzheimer's and so on works. Rather than me just standing here saying, this, and these are the side effects, I thought it'd be better if you actually knew how they worked. So I'll try and explain that bit. So that was my general plan. So, do we know about the brain? Yes. It is the most important organ we've got, according to the brain, that is. Can I just move this slide? So, anyway, right, brain cells. We've got about 10,000 million brain cells. Well, we start off with that. It does go down, but not as much. So there's the brain cell, there's a nucleus in the middle, there's fibres and filaments in there. You've got these nerve fibres going off at that direction, and then you've got impulses coming into the brain cell from here. You've got blood vessels keeping it all alive and ticking. And then you've got these astrocytes and microglial cells, which just sort of help give support. So that's what a brain cell roughly looks like. Now this is the important thing, this bit here. It's called the synapse. But this is what the healthy brain should look like. So the blue dots are the synapses, and the green bits are the cells, and these are the nerve fibres going off in different directions. Each brain cell has probably got 500,000 synapses. So if you want to multiply 10,000 million by 500,000, that's the number of synapses we've got in the whole brain. It's a lot. More than the number of grains of sand around the British Isles, I've been told. But I don't know. So anyway, that's what it looks like. Anyway, 10,000 million brain cells. Messages are passed from one brain cell to another via these nerve fibres going through the synapses. It's a little bit like an electrical Mexican wave that goes down the nerve fibre and reaches the synapse at the end. Now the synapse at the end is the junction between one brain and another brain. So this is what it looks like. So you've got a brain cell over there, sends a message along the nerve fibre to here. When it gets here, you've got little vesicles in there. Those vesicles have got little chemical in them, which could be something like dopamine or serotonin or histamine or acetylcholine, something like that. There's a gap between that synapse and this synapse, and on that synapse there's some receptors on there which are specifically designed just to accept that transmitter. So what the process is an impulse arrives, it zooms down here, as it gets there, so these vesicles fuse with the end plate, transmitter is released, hits the receptors the other side, the receptors change shape. As they change shape, that creates a trigger, which then causes a change in the electrical part of here, and then the impulse goes off over that direction. The spare transmitter is taken up into the nerve endings, and then it all resets itself. That takes about thousandths of a second. And the interesting thing is that's the same in humans, it's the same in your liver, your kidneys, your heart, your skin, your brain. It's the same in humans, monkeys, rats, toads, monkeys, the lot. It's the same everywhere. It just gets more advanced the further you go up, the further you go up the evolutionary tree. So that's the way in which brain cells communicate with each other. Now, one of the things that we can do with with that is if we can get a drug in there, a chemical in there, then we can influence, we can change the way those brain cells are talking to each other. So, of course, none of us would do anything like that, would we? He said, having a swig of caffeine, coffee, which contains caffeine. Caffeine gets into there and actually stimulates that, which is where caffeine has its stimulating effect. If you were to have some cocodamol, for instance, which has got codeine in it, they'll go into there and they'll block some of the receptors. So lots of chemical, nicotine will, if anybody smokes. Alcohol will get in there as well. So we've already discovered as human beings that this is the way to affect the way our brain works. Now, I won't go into this great detail, but there are about 200 different transmitters, chemicals in those vesicles at the end. 200 different ones. Each nerve ending has only got one type. So a nerve ending will either have dopamine, or it could have serotonin, or norepinephrine, or acetylcholine in it. The receptors on the other side will be designed just to accept that. So you've got dopamine receptors. Dopamine is released, it'll hit dopamine receptors. Acetylcholine is released, there'll be acetylcholine receptors. The point about this is that all these different transmitters they do different things in the brain. So dopamine, for instance, is not much in the body, but in the brain it's involved with movement, and that's the bit that goes wrong in Parkinson's disease. So in Parkinson's disease you get less dopamine produced by the brain. You get less dopamine, so therefore dopamine is the one that tells your muscles to relax. So as you get less dopamine, so your muscles tighten up, and that's where the symptoms come from. And therefore one of the treatments is to give people essentially something a bit like dopamine, and therefore you give the brain a message that it's okay to relax your muscles. So that's where Parkinson's comes from, but it's an imbalance of chemicals in the brain. Dopamine's also the part of the brain that takes information in, processes it, decides what's important, and then decides what to do about it. Now, if you've got too much dopamine in your brain, then that part of the brain can start to get overactive, it can start making things up, it can start putting undue importance on something. So the fact there's a chap walking around out there, now if I knew there was £100 on there, I would think that was important, because he could have nicked it. But as it is, it's a centre here, so there's probably somebody wandering around what's going on. So that's my brain deciding him being out there isn't important. But if you had too much dopamine, I might start thinking, hey, that's worrying, and have they closed the curtains because somebody's out there about to attack me. So if you've got too much dopamine, this is where psychosis comes from. And if you were to go home tonight and smoke a huge joint, this is not a recommendation, just in theory, were you to go home and smoke a large amount of cannabis gets into the brain, it stimulates cannabis receptors. Now there's an interesting one. What have we got cannabis receptors in our brain for? We've evolved over the last 2 billion years to have cannabis receptors in our brains. And nobody's very sure what they're doing there. But that's a separate thing. Anyway, if you were to do that, have a lot of cannabis, that stimulates dopamine, which would then make you go psychotic. So too much dopamine in one area of the brain, you become psychotic. Too little in another area of the brain, and you can have things like Parkinson's disease. Serotonin regulates mood. Noradrenaline's blood pressure and arousal and so on. But acetylcholine is the interesting one here, because acetylcholine there's a lot of acetylcholine, so all the nerves with acetylcholine in them are there, and they help regulate memory. So you use acetylcholine in the brain when you're trying to lay memory down, remember things, when you're trying to recall memory, spatial awareness, social functioning, reviewing what you've done to see whether you've done it very well, and if you didn't do it very well, can you do it better next time? So it's all that types of things, and it is acetylcholine. When the brain begins to suffer from dementia, there seems to be a drop in the amount of acetylcholine in the brain. There are lots of other changes, but acetylcholine is the big it's the major drop in the brain. So because of that, if you haven't got enough acetylcholine, then you haven't got enough ability to be able to learn things, remember things, lay down memory and so on. The other one that's GABA is the inhibitory one in the brain, so that's the brake of the brain, and glutamate is the accelerator, so that livens things up. So all I'm trying to say is that if you haven't got enough serotonin, then you get depressed because your mood goes down. If you haven't got enough acetylcholine in the brain, then you can't remember things very well, put memory down. If you've got too much GABA, then you're sort of very quiet and sedated. And if you've got too much glutamate, that overexcites the brain. So what I'm trying to say is that all of those transmitters, and there are loads of other ones, if you've got too much or too little, that makes a difference to your brain. So we've done all that, haven't we? Yeah. So as we get older, and let's face it, if you look at evolution, anything the human being does after about 40 is a bonus, really. We're not, once we've got past reproductive stage, everything else is bonus now. I've got my old person's rail card, so I do know that. I do realise, but hey, anyone else got one? Oh, they're brilliant. Third off all rail fares. That's fantastic. You've got a station here as well, haven't you? So that's all right. So as your brain begins to get old, then this is what the brain cell looks like to start with. So you've got the brain cell there, you've got these nerves going off in different direction, impulses coming in, and then generally there's a long nerve fibre here. At the end of it, these dendrites go out, spread out, and pass messages on to other bits of the brain. So if I decide to move my hand, then one part of the brain will say, right, contract this muscle, relax that one, and then the message will go down these long things, and eventually they will get to the nerve. Unfortunately, what happens as you get older is that, first of all, some of these start to break down and they start to get sticky, a stickiness on their surface. And that means every time your brain moves, then they sort of stick to each other and then they get pulled off. And so you get what are called tangles, which are where the nerves are broken and they're all stuck together and they don't actually work. So the messages that you can pass are much reduced. You also get tangles up here as well, and you can also get what are called plaques, which are sort of areas of just sort of stuff. It's actually aluminium silicate, which then, when they move around, they cause these lot to start sticking together. So that's a tangle and that's a plaque. That's what it looks like in a microscope. And just if that's one of the nerve fibres, what they normally look like is that they've got some tubes running down them, which are ones that will take food down to the end, a nutrient, will send transmitters down there and so on. And it's this protein, this tau protein, which seems to go wrong. It starts pulling apart. And then it doesn't stick these together, and then some bits of it will come out the nerve fibre and go elsewhere and start sticking to other ones. So there's something wrong with the way in which the nerve fibres themselves begin to break down. And also, you also get these proteins here which can stick together, which then causes the plaques. So there are lots of things which are happening in the brain. And the drugs which we have to help an ageing brain aren't really very good at the moment. It's a great shame. But what we could do is we could try and stop the enzyme that causes all this, the enzyme being made which breaks all the nerve fibres off. We could try and have a drug which helps clear the plaques. Now there is one which is called solanezumab, which always looks to me like it ought to work better in reverse. They look quite promising, but the trouble is some of these have been tried and they clear the plaques, but it doesn't actually do anything. It just gets rid of them. You could stop the tangles. Nobody's worked out a way of doing that. Or the only other thing we've got really is to boost what's there or stop it getting worse. But the amount of money and research going into this is astonishing. Unfortunately, you can just see it there, but there were, believe it or not, 413 drugs which have got to tests in humans in the last 10 years. None of those have got to the market. So there's you think, well, we ought to be coming up with better drugs. But honestly, people are trying. They either don't work or they've got too many side effects. So it's a bit frustrating that we haven't really got much further. The drugs that we have got, I'll just go through those briefly. So we've got the acetylcholinesterase inhibitors, which just rolls off the tongue, doesn't it? No, it doesn't. Yeah. So we've got donepezil, galantamine, and rivastigmine are the three that are available in the UK. I'll mention memantine, and there are some other drugs which are available, which can help sometimes. So those are the three. Donepezil was the first one that came out. Galantamine was the one that was developed from snowdrops, was it? Snowdrops? Something. Yes, yeah. That was found in those. So all three of them are available. They're all fairly cheap now, so there should be no problem with anybody prescribing them. So what they do is, okay, this is what your normal nerve looks like. The only thing about I'm going to talk about acetylcholine then. The only thing about acetylcholine is the only transmitter that isn't taken back up into the nerve endings. And what happens is you've got some enzymes here which break down the transmitter to stop it leaking out and stimulating other nerves. So if that's what it normally looks like, now what seems to be happening in dementia and Alzheimer's is that there's less transmitter, there's less messages getting through, there's less transmitter, there might be less receptors, general deterioration in the activity. It's about like if you imagine a car with old leads going to the engine, they're all beginning to break down, there's not much spark getting through. So what those three drugs, donepezil, galantamine, rivastigmine, do is that they block this enzyme up here, which is the cholinesterase enzyme. So these are the cholinesterase inhibitors, so they inhibit the cholinesterase enzyme. And so when the transmitter is released, then the transmitter is released and hits those receptors there. Because you stop the breakdown of it, there's more transmitter around, so you're boosting what's already there. So you're not actually really changing very much. It's a bit, if you want the car analogy, it's a bit like WD-40 in your nerve endings. It's making the most of what's there. It's not creating any more, it's just making the most of what's there. And so when you've got transmitters then released, you get loads more of it because there's still some left over from the last time. So while the nerve is actually working, then it will try and make the most of it. And that's really all they're doing. They're helping make the most of what's in the brain. They probably don't really slow down the process, unfortunately. That's what these newer drugs are trying to do. But if you imagine, somebody's brain function is going down gradually like that, what these drugs seem to do is they'll sort of stabilise it for a bit before it starts going down again. So you make the most, you put the clock of, you stop the clock for a few months or years, and then but the interesting thing is that if you then stop them, then you'll tend to go down to where you would have been without them in the first place, if that makes sense. So they're not really doing much in the long term, but they're all we've got at the moment. They're generally quite easy to use, quite reasonable doses. Some of them are available as patches, some as liquids, some as melt-in-the-mouth tablets. So if someone's having difficulty swallowing them, you can switch between them fairly easily and find a different way of taking it. So those are used throughout the whole world, and they're all we've got at the moment. Sorry?
You skimmed over memantine.
Oh, I'm going to do it now. I'm going to do it now, right? Yeah, I was definitely coming back to it. But by the way, if anybody's got any questions, please attempt to interrupt me.
How successful are those?
How successful are they?
In terms of 1 to 10?
In terms of 1 to 10, they're probably, it depends how. I think one of the big problems with testing these drugs is that we don't. Is that you can do the tests on daily functioning and those sort of things, but I don't think they quite measure really the sort of the subtle effects that they have of helping somebody cope. So I mean on a scale of 1 to 10, they're probably about 4, perhaps. So yeah, they do definitely work. They don't work in everybody. And the thing is, you don't really know whether they've worked unless you stop them, which then is, then you deteriorate. So it's a difficult thing to do. Yeah, I mean, they're not wildly successful, and I'm sure in 100 years hence, they may still be around as a help, as one of the drugs you could take.
Just a question, how is it assessed? Just blood? Taking blood will give you the information about the receptors?
No. Unfortunately, no, that is one of the holy grails, would be to find a test, because if you could do that, you could do a test for schizophrenia and depression. And so all of these things are based on scans of human brains, they're based on animal studies.
Speculation.
Well, it's speculation then proven by saying if that is true, then if we do this, it must be then, and it does this, then that must be the cause of it. So yeah, actually the trouble is getting human beings to agree to take tests like having bits of your brain taken out it's not so easy to get volunteers for those tests. So yeah, it's a bit of a shame. So anyway, memantine, which was in use in Germany for 25 years ago, is slightly different in that what we know in the brain is that glutamate is the excitating transmitter, so that winds the brain up. And GABA is the brake, so you need lots of glutamate to keep the brain going. However, if you have too much glutamate, it can overexcite the cells. So if you've got glutamate, say this was glutamate, but if too much glutamate here excites the cell too much, and if you excite it too much and it's a bit vulnerable, then it can get overactive and you can end up by killing it off or damaging it. So glutamate is quite important. You don't want too much glutamate. In fact, glutamate may be one of the reasons why schizophrenia occurs. So if you've got too much glutamate in there, it'll overexcite and damage brains and kill off brain cells, and that's the one thing you don't want in an aging brain, is killing off brain cells that you don't need to. So what memantine does is it goes into these receptors and blocks them. So therefore, even if you've got too much glutamate, you reduce the effect of too much glutamate by blocking some of the cells. You then don't overexcite the cells, and therefore you don't kill them off quite in the same way as the glutamate had done before. So again, that's not really doing much in terms of the long-term outcome, but it is helping making the most of what's there, if that makes sense. So yeah, you're just getting a lesser effect. That's actually how most of the antipsychotic drugs work. They do the same thing, and they block dopamine receptors. So that's the two major groups of drugs we've got. I think when the new ones come out, they are going to be horribly expensive, because if you imagine how much research work has gone into the previous 413 drugs, that's an awful lot of money wasted. So when one does come to the market, there's an awful lot of costs. So those are the main ones. Now we've got the adjunctive treatments or add-on treatments. Sometimes antipsychotic drugs may be useful. So I guess some of you will have come across risperidone, perhaps, quetiapine. All of those drugs block dopamine receptors. So if you've got too much dopamine, you can get psychotic. They're also, some of them are quite tranquilizing in a calming, tranquilizing is the wrong word, sorry, I'll withdraw that. Can you edit that out of there, please? Calming is probably the best way of doing it, because they can be a little bit sedative. Some of them are antihistamines, so you get that whole antihistamine type sort of calming effect from it. So with those antipsychotics, if somebody is very disturbed or aggressive or upset all the time, sometimes a really small dose of an antipsychotic can help. as a sort of late, you know, if nothing else has worked.
Sorry, in the Alzheimer's Society report in 2009, they criticised the use of antipsychotics for dementia, especially in hospital contexts. You talk about
Yes.
managing aggressive behaviour, but doesn't it sedate patients to a point where actually it increases falls risk and compromises things like balance?
Right, I'm glad you asked that question, because I'm going to deal with that right now. Because there is one thing that all of those reports have missed out. They've ignored a whole bunch of research that doesn't fit their theory. And just in case you're interested, that's Dr. Alzheimer, as in Alzheimer's disease. And that's Dr. Levy. It looks like Louis, but I'm just being posh. That's the Russian way of saying it. He was the person who discovered Lewy body dementia, Levy body dementia. Just thought you might be interested in that. They both worked in the same lab in Russia. Now, this, as you just quite rightly pointed out, there's lots of stuff here on, you know, don't use antipsychotics for more than 6 weeks, and that was the report, the Banerjee report. Spooky, eh? Thank you. I didn't pay you to make that comment. You are a cool cat, though. So, and quite rightly, they said there is a lot of problem with antipsychotics being given just to calm people down, to shut people up, keep quiet, and I quite agree with that. However, there are occasions when a small amount can help. Now, what you'll see from there, it says don't use short-term treatment up to 6 weeks. Now, the one thing that they've all missed out from here is that, and I've cut this right down, is that the increase in falls and deaths and strokes and so on is all in the first 2 weeks. That's the number of events, and that's what you'd expect normally. It's all in the first 2 weeks. And there's another study which shows it's all in the first month. So this thing about don't use them for more than 6 weeks is wrong. If you got to 6 weeks, you're okay. It's the first 4 weeks the important bit. So what I would say is that if you or anybody you're caring for, or relatives, or whatever, is offered one of the antipsychotics, usually risperidone and quetiapine, then one thing I would say is, obviously only if really needed, start with a low dose and go slow, and use the lowest possible dose. And if something doesn't work, then stop it, or if the person seems to get worse, stop it. But during that first week and 3 or 4 weeks, make sure that they're drunk enough and have moved enough, because that seems to be the two major causes. So it's not what I think they missed in those reports was saying, wait, you know, start it and then review it at 6 weeks, or stop it at 12 weeks, rather than start it and make sure you really look after the person in those first couple of weeks, because that's the time it's been prescribed, so there must be something wrong there. So making sure, I completely agree with the report in that not using them too much, and you know, one nursing home can have 20 people on an antipsychotic and the next one have none. So
yeah, I work in a care home. We have a lady on risperidone.
Yeah.
But again, like I say, it has to be monitored very, very closely and make sure the dosage is definitely given at the right spacing, because they do become very, very drowsy. It is a sedative.
Yes, that's right.
And that is when they're likely to increase your
and what you can also get is what's called postural hypertension, which is when you stand up and feel dizzy and fall over, which is where the fall bits come from. Risperidone's not so bad at that.
Personally, I work nights, and that's when they're normally given at night time to sedate them, because if they're wandering, with the dementia unit, but they are very dangerous, I believe.
Yes, if they're not used properly, yes. Yeah.
I think
but
for
others,
it's in the care home, it's managed and
it's managed and run.
Yes.
Quite reactively.
Yeah, and in fact, things like memantine and donepezil and so on can sometimes have just as good an effect on someone's behaviour and managing that and keeping them safe as can an antipsychotic. But yes, actually keeping the dose really low, really low is very important. Antidepressants, if someone's depressed, I'm running out of time, so sorry. Antidepressants, yes, if someone's depressed, treat the depression. I don't see what's wrong with that. Oh, you can't read all that. Fantastic little magazine. Before I started on Prozac, they used to call me Grumpy. I missed one. That was another one. There's two blokes on a veranda in America. One's playing the guitar and the other one says, Or the chap playing the guitar says, it's these damn Prozac, I haven't had the blues for weeks. So if somebody's depressed, and of course you're not always going to know whether they're depressed either, so I think that's sometimes worth a go. Now sleep, when it gets dark, when it's light, the light stops your brain producing melatonin. When it gets dark, then your brain starts producing melatonin because it's got dark, because it's saying now's the time to go to sleep. Melatonin is what you produce in the brain to tell the brain now's the time to wind down and get ready for sleep. So as you get older, you get less melatonin produced, so therefore it can sometimes be more difficult to go to sleep. So what you can do is take melatonin by mouth, which then boosts the amount of melatonin in the brain, can help some people go to sleep. The trouble is, circadian, which is the main one that's available, there's a limit of 16 weeks on treatment, which is bonkers. There is no reason, there's a legal reason why you don't do 16 weeks, but actually there is no harm in carrying on for a lot longer than that. There is no evidence that melatonin is harmful long term, it's just that no one's done a long-term study and tried to get a license for it. And if GPs won't prescribe it, get someone to go on the internet for you, because you can buy it. You can buy it over the counter in America.
No, I was going to say that.
Yeah.
I've got our cupboard full of it.
So if your GP won't prescribe melatonin, I'll still call it down here, we'll sell you some.
My sister-in-law went to the States and said, I'll get me some melatonin. She came back with a whole case of it.
Yeah, you have to be a little bit careful. Some of them are animal-derived melatonin by not very slightly sordid ways.
If I sleep over there.
Yes. So you can buy it over the internet quite legally if your GP won't prescribe it. One thing I would say is don't watch too much television at bedtime, because that's what normal sleep looks like. This is what our sleep looks like. Instead of getting this nice hour and a half wave form in there, you get lots of disruption. That's your dreaming bit, that's waking up at the top there. So our sleep tends to get more disrupted as we get older. And so during daylight, the blue light that the blue light that's out there is what's stopping the melatonin being produced. Now the trouble is, if you look at a television screen, anything with a backlit screen, so televisions, computers, iPads, mobile phones, those sort of things, they produce, that's the wavelength of the light they produce. And you'll notice that lots of blue light, the same light that stops your brain producing melatonin. And I don't know how well you can see that, so that was a photograph of someone's slide. But this is somebody's melatonin level going up at night time. Then they were exposed to an hour's worth of television. And you can see their melatonin went right down, and the television was turned off, then it comes back up again. So it's actually quite, watching television late at night can make it difficult for some people to go to sleep if you're a bit low on melatonin. Two ways around this, one of which is to turn the brightness down, because it's dose dependent. The other thing to do is just to get some, I bought some for £5 off Tinternet. Just get some yellow or orange glasses. I've got clip-on ones. And what that does is it takes all this lot out. Just gives you that bit. So it means you've got more melatonin. So it's just a simple thing. If someone has difficulty sleeping, particularly if they're older and has less melatonin, that way makes the most of your melatonin.
I've actually got a free app on my computer that turns the...
Right, that's... Yes, you... Yeah.
At night time.
Yes. Yes, you can get programs. I've talked about this to students at UEA. Some of them said they've got this program. So yeah, that's So you actually it doesn't work on television, so does it? No, but it's a great idea. So if someone has problems sleeping, just try this rather than going to drugs. There are other drugs, the Z drugs. Zolpidem, I think Zolpidem is great because it works quickly. It doesn't last very long, rather than some of the other ones which last quite a long time. So other drugs, ginkgo biloba, it's fairly harmless, probably doesn't do very much. Folic acid, no evidence that works. Omega-3 fatty acids, again fairly harmless, unless you want the smell of fish. Non-steroidal, so that's treatments for arthritis and the like. Jury's out on that one at the moment. And statins, people are unsure about that one as well. So I would generally advise that there's no cures at the moment, and lack of effective treatments is not due to a lack of effort. Medicines can help you make the most of what's there, but start low, go slow, and if it doesn't work, stop it or reduce the dose. And what we're aiming at doing is slowing the decline, helping everyone cope, and making sure people get some sleep. Because if you get some sleep, it's amazing what you can cope with sometimes. But if you don't get sleep, it's terrible. Right, okay, that's it. Thank you very much.
Thank you.